And I need to no, I actually did that already, isn't it? I hope you saw the other lectures that I uploaded on my YouTube channel. Yeah, so this, as you can already guess, this type of corrosion is especially harmful to alloys that passivate by forming a protective surface film. The case of aluminium. So with that constant flowing of water and abrasion that is happening, it means that every now and then your aluminium has to form a new oxide layer. Okay. And it just may, after it erodes the fume, it may leave it exposed for a time that may even allow for some corrosion to happen. And if the coating is not capable and rapidly reforming as a protective barrier, corrosion may be severe. So like we said, if you had an oxide layer on your metal formed before, and then that layer is disturbed and your metal is exposed, your metal is going to corrode at what rate? 10,000 times. It is 100,000 times faster than before that fume was formed on it. Relatively soft metals such as copper and lead are also sensitive to this form of attack. Usually can be identified by surface grooves and waves having contours that are characteristic of the flow of the fluid. So even just on the metal, you see small like kind of waves depicting that flow of the fluid, or contours that are depicting the characteristic of the flow of the fluid. Corrosion, erosion, as you can guess, also is commonly found in piping, especially the one that bends and changes in pipe diameter. So if you've noticed, usually in piping, the ones that are usually replaced, the pipes are usually the connectors at the bends. Why? Because that change in direction of the flow of the liquid, when your liquid is flowing, isn't it, along a pipe, before it comes to a bend, the water will not just get less bend like that. It first hits the connector, or that part of the piping where they have the connector in place. So it first hits the connector straight on, and then that's when now it changes direction and maybe moves to the left, depending on where the pipe is, or the left or the right. So usually it's at that point where at the bends, that's where you have corrosion happening, or where there are changes in pipe diameter. So with changes in pipe diameter, we know that the pressure also changes. So where you have increased pressure, it means now you're increasing the abrasion. The risk of abrasion becomes even higher where you have change in pressure, or the turbulence that happens that area where you have the turbulence, where you have the bending happening, or the change in pipe diameter. That place where you have your turbulence happening of the water inside the pipe, that is the place that is highly susceptible to this type of corrosion, which is erosion corrosion. Also with propellers and turbine blades, as you can guess, at the stations where at the Kariba there, where we have our huge turbines there turning, and where we have our pipes, also our pumps also. This form of corrosion is also most likely to happen because they are working with water that is coming under very high pressures. So which is the best way to reduce this type of corrosion? How do you reduce it? So you change the design to eliminate fluid turbulence effects. If you can change the design of your piping to eliminate fluid turbulence effects, for example, if the bending is unnecessary, try and make your pipes as straight as possible and avoid unnecessary bending of your pipes. So this is an example. As you can see, this is a piping, isn't it? So your water is flowing from this direction, for example. So when it's coming this direction, it will first hit this point before it forms turbulence here. That's when it now realigns itself to the new direction, which is downwards movement. So it will be horizontal. It's here, this will be a turbulence point here, and then that's when it comes down. So as it's hitting this part every time, there's abrasion happening, there's wear happening in this area. Till finally you just see a hole here and you have your leakage. With a high temperature there, you have the water now spouting out as a result of this corrosion here. Then the 8th one here is stress corrosion, sometimes termed stress corrosion cracking. This results in the combined action of an applied tensile stress and a corrosive environment. Both influences are necessary. So what is necessary for this to happen? You need to have, there has to be an applied tensile stress as well as a corrosive environment. And some materials that are virtually inert in a particular corrosive medium become susceptible to this form of corrosion when a stress is applied. So you find, for example, a metal in a salty solution may not be highly susceptible to corrosion. But then when that metal is put under pressure within that same solution, it suddenly now becomes it starts to corrode. And this type of corrosion is what we're calling the stress corrosion. So small cracks form and then they propagate in a direction perpendicular to the stress, forming a failure. So failure behavior is characteristic for a brittle material, even though the metal alloy is in fact ductile. So the failure behavior is characteristic of that for a brittle material, even though the metal alloy is in fact ductile. So we find that a metal alloy will be ductile. But then when it's exposed to this particular type of environment, it actually becomes brittle. It changes under, with not just exposed to that environment, but then under stress and exposed to tensile stress. So as you can see this bar here. So this bar under normal conditions, just like anywhere in your house, it will not, for example, form these cracks. But then when it's bent like this and then put in a salty solution, for example, or an acidic solution, it now begins to corrode at the bend. You begin to see these cracks at the bend just before failure. This is an example of stress corrosion. So I think for today, this is about it. So this is more just stress corrosion. I'll send you this slide so that you have a closer look at the different types of corrosion. But for me, what's important now is that if you can know the different types of corrosion, okay, if you can list them, at least, if you're able to apply the earlier formula the first formula that we began with, that is the rate of corrosion. I think that's enough. I understand that this material is quite bulky, though I know it's also easy to understand, but it's generally quite bulky. So what's important, like up to where we've reached, is just to know the types of corrosion. If you can briefly explain each type of corrosion, and then if you can be able to apply the formula. So we'll do 1 or 2 examples in class, and then I think we're good to go on this one. I'm just looking for the formula here, this one. The corrosion penetration rate, the CPR. And then we're good to go. I'm sure things like this you can't forget. passivity. When a question comes, what is passivity? I'm sure most of us, even just from this, just from here, we're able to explain what it is. Let's look at, let me just quickly, maybe before we end our lecture, let me just open the paper that, the session that the full-time students sat for 2 weeks ago. Let's see the questions that came on corrosion and see if we are already able to answer them. I think everyone has this paper. I emailed it to most of you and asked you to share on your WhatsApp group.
Yeah, I haven't seen it.
Pardon? You have not seen it?
I haven't seen it. I didn't, no.
Sure. Is Steven here? The class rep. Okay, I'll ask him to send to your WhatsApp so that everyone has a copy. Are you able to see my screen now? I have question 5 here. Are we able to see the screen? I've moved away from the lecture presentation. Are you able to see?
Yes, we can see.
Okay, all right. So question 5B here says, briefly describe any one of the 2 techniques used for galvanic protection. Does anyone remember what we talked about? Remember galvanic corrosion? Where 2 metals will behave as if they're in a lab, as if they're in the beakers and there's electrolysis happening. Now saying that, like in reality, we actually have, you don't even need to have a beaker and you have your voltmeter there and everything happening, no. But as long as certain conditions are met, if there's a solution that is able to accommodate the transfer of electrons, and if you have 2 metals that are far from each other in the galvanic series, or basically one that is more reactive than the other. So now how do you control? So we said what? The anodes should have a greater area, significantly greater area than the cathode. Remember that. That was one of the points. Where you have the similar metals. Anyone remember the other points there that we talked about for galvanic protection? Let me just get to the slides. Let's look at it again together. Okay, so we're back on the slides. A number, I hope we're able to see it now. Are we able to see the slide? Share we?
Yes, I can see the slide.
Okay, yes. So here it says a number of measures may be taken to reduce the effects of galvanic corrosion significantly, including the following. So these techniques are generally described into two. There are two main. As you can see, these ones are similar and these ones are also similar. Okay, so they're basically just two techniques: electrically insulating them or coupling of dissimilar methods. So this is what the question was just. So you just any one of these was enough. It was well answered, at least. With this one, we didn't have much problems. Let me see if there's another one on corrosion. Oh yeah, so the corrosion penetration rate, CPR of materials is expressed as follows. So you have your formula there even given to you. You don't even need to memorize it. Everything explained to you. Then the question comes, a thick steel sheet of area 500 centimeter squared was exposed to air near the Indian Ocean. After a 1-year period, it was found to experience a weight loss of 405 grams as a result of corrosion. Steel density is 7.9 grams per centimeter cube. Calculate CPR in millimeter per year of the steel sheet. So already this constant is picked for millimeter per year. So your K is given already. So you place your K there. Weight loss in milligram. So now, because sometimes we tend to panic in exams, you don't even want to check the units there. So you can see here, weight loss is in what? Milligrams. And the one that is given is in grams. So you have to convert this 405 grams into milligrams and place it there.
Sorry, Doug. Please share the screen for
Okay. Is it much better now? How about now?
Not yet.
Much
Can you
better?
share the screen for the question?
No. Can the screen for the question?
Oh, you can't see the screen. Oh, sorry, I left you. Okay. Can you see it now?
Yeah, still on the
Yes.
And it will change.
Yeah.
Okay,
Still.
so we have this question. The corrosion penetration rate of materials is expressed as follows. So you're given the formula, like in this case, they were given the formula. Everything nicely explained. As you can see, you have a constant here. And then you have your question here. A thick steel sheet of area 500 centimeter squared was exposed to air near the Indian Ocean. After a 1-year period, it was found to experience a weight loss of 405 grams as a result of corrosion. Steel density is 7.9 grams per centimeter cubed. Calculate the CPR in millimeter per year of the steel sheet. So like we said, K depends on the unit that we're using. So here we've been asked in millimeter per year. So meaning this constant, you get it as if it is for millimeter units. So you put your K there, 87.6 in the numerator. Coming to the W. W is weight loss in milligrams, as you can see here. But sometimes because of panicking in exams, we failed to read questions correctly. I always tell my students, if the examiner is kind enough to even provide you with a formula. It's not because it's Christmas or what. Just know that somewhere, somehow, there's a catch. Don't rush to now solving and thinking that it's the easiest question. No, look at the units usually. Okay, conversion of units, usually that's where the problem is. So some students were just getting 405 and placing it here. But what does the formula say? It's weight loss in what? Milligrams. So I'm supposed to convert this 405 into mg and place it there. Then you have your density, gram per centimeter cubed, and you're given in gram per centimeter cubed. So take it as it is, place it there in your denominator. You have your A there, exposed specimen area in centimeter cubed, centimeter square, sorry, and you have it in centimeter square. So you take 500 as it is, place it there where there's A. And then you have your time. Then you calculate. So it's a 1 year period. So again here, if you solve these questions before, you know that time is what? In hours. So what do you do to your time here? Your time is a 1 year period. Richard, what do we do here? Is
Maybe
Richard
it will
there?
be 24. 24.
24 times? Sorry, I think you are breaking there.
Or 24 times 365.
24 times 365. Do we agree, Kunda?
I'm the one who made that proposal.
That's fine.
Oh, it's actually you. Okay.
Yeah.
So obviously you agree with what you're saying. I thought it was Richard I asked. Okay, Fales, what do you think?
It can, madam.
Okay. So now in the exam, I had students multiplying by a 1 here. So they just simply put their area and then multiply. They even put it in brackets. They're even kind enough to put it in brackets, the 1. So that I should know that you know, but then you obviously know that here, if it's saying exposure time in what? In hours. So 365 times 24. That's the value that you place in the denominator. Then you calculate and get your final answer. So sometimes it's not because, I think sometimes it's just panicking. I don't know. I think it's just exam pressure. Maybe that makes people not do the right thing. So please try and be as composed as possible in the exam room. So this is an example of how a question can come like this. So like I said, go through this, expect a question like this in your exam. Okay, so unless there are any questions, I think we're done for the evening. So metallurgy students, are you on campus already?
Not yet, but we are supposed to be in campus by Monday.
By Monday?
Monday, Tuesday. Yes. Because
Okay.
Tuesday we have a class here.
Yeah, I think we have a class. I have a class with you on Tuesday, isn't it?
Yes.
Yeah, so I'll see you Tuesday. Then for purchasing and supply, and the production management, I don't know if we have, I don't remember if we have production management students. Anyway, purchasing and supply, I'll see you from the 4th, between the 4th and the 7th of November. That is when our classes will begin. So
For us, it's from the 8th, madam.
It's actually from the 8th. And not from the 4th?
We are only in campus on the 8th.
Okay, all right. So I'll see you from the 8th. So meaning for now, we've exhausted our online hours. What's left is physical. So this is our last online I was supposed to give you an assignment. Like I said, I wasn't able to do it, but we have a week. We have a week left. So if I have to give you this assignment, then I have to give you a test. Anyway, I'm still thinking about that. I'll see how I'll do it because I think we only have basically 1 week left before the 8th, isn't it? Oh, no, 2 weeks. Anyway, I'll see how it goes for purchasing and supply. Maybe we still have time for one assignment. Maybe we can still squeeze an assignment there. With metallurgy, maybe I can still do that within a week. Let me see. Let me just try and see how I'll do it so that it's fair to both groups. So unless there are any questions, I think we're done for the evening. Pardon? Hello? All right, we call it an evening. Good night, everyone. I'll send you the lectures, the PowerPoint presentation for tonight. And I think the others that I didn't send you, Steven sent me a list. Though his list includes some that I sent you already. And I'll still resend them. That's the same thing. So have a good night, everyone. See you on campus.
Thank you, Doc.
See you on campus.